Right, hello everyone. Welcome to the ECR seminar. Today we have Dhong Yeon Cheong from Yeonsei University. He's currently a PhD student in Yeonsei, and today he's going to talk about inflation and the standard model, Higgs R-squared inflation framework. So Dhong Yeon, please start when you're ready.
Right. Slight problem. I have this meeting record thing up. Is it okay for you guys? I mean, can you see the whole screen?
Yeah.
Then
Oh,
okay.
can you press got it in the box?
Yeah, but I don't see my pointer right now, so I guess I can just go on. Okay.
Uh,
Yeah.
right.
Great. Um. So yeah. Thanks, Guihan, for the invitation to give a talk at this seminar. It's a bit unfortunate that I am currently abroad right now, and I couldn't attend and give the seminar in person, which I really wanted to. But hopefully, I can visit CasKASI at some point and also discuss with you guys in a in-person format as well. So yeah, today I will be talking a bit on some of the topics, two papers that I've done during my PhD at Yeonsei, on basically trying to look at the interplay between inflation and particle physics, mostly in the standard model context, which I dubbed the Higgs R-squared inflation framework. And this work has been done mainly in collaboration with Cass Corey in Japan, Sung Lee, who was a PhD student in Yeonsei and now is a postdoc at KAIST, and my advisor, Sung Chan Park. So yeah, with that, let's dive in. So the start of the motivation, I would like to just throw out the standard model right now. So the standard model of particle physics has been well established in the 20th century, and up to this day has been extensively tested in terms of experimentally and also theoretically, with the highlight of the experimental tests and confirmations coming from CERN, the LHC at 2012, with the discovery of the Higgs boson, which is a scalar degree of freedom that is um, thought to be fundamental in a particle physics context. And from there and up to now, we have extensively tested this, and we know quite a lot about particle physics, know quite a lot about what is the context of particles in our universe. And we have know all of these properties in the sense that we have basically a very broad knowledge that can be summarized into a book. Let's say the review of particle physics, which you can see is like 1,000 pages. So it's a very, very vast amount of information that we know about particle physics in that standard model. But still, even if we know so much about the standard model right now, there are still things that we don't know about particle physics and the standard model these days as well. So there are a lot of unsolved questions that the standard model cannot give. And if I just highlight some of them, will be dark matter. We know we have a lot of observational evidence for dark matter. We know a lot about the properties of dark matter. However, in terms of a particle physics context, or just in general, we don't know really what the origin and what the composition of dark matter is in our universe. Same thing goes for dark energy. We have observational tests, we have observational evidence for a late acceleration phase in our universe. However, we still don't know what is the origin of that. Is it a vacuum energy? Is it a slowly rolling field? We still really don't know what the origin of that is. Baryon asymmetry. We now know that matter and antimatter diffraction is quite off, and in order to have that, we need to have an asymmetry between baryons and antibaryons in the early universe. We have a lot of mechanisms to make this happen, but still we don't know what is the mechanism that is responsible for our universe. Inflation as well. We know quite a lot about inflation. It's a very successful paradigm. However, in terms of the origin of what is responsible for our cosmic inflation in our universe, we still don't really have a clear answer to that. And of course, there are many more that are not highlighted here. And just for a personal choice of interest, I would like to focus on these two. during my talk, mostly on dark matter and also on inflation. Just try to tackle these two questions and see if what we can do with this in terms of like a particle physics context as well. Right. So with that, let's just slightly dive into why I'm interested about dark matter. So if we just look at like this figure, schematic figure from SNOMAS 2013, we can see that there is like a lot of models and a lot of things that can be a candidate for our dark matter. You can see models that are based on supersymmetry. You can see that there are some non-thermal things that can act like a wave. There are also like non-particle dark matters, like compact objects, and one of those can also be primordial black holes. So definitely, we don't have like a shortage of what can our particle physics, what can our dark matter be. And in order to specify what is the main component of our universe, it's still quite a hard task. And a way to show this again is actually looking at the mass range of how broadly, how wide the mass range of dark matter can be allowed in our universe. You can see that at the lower end, it can be 10 to the minus 22 electron volts, which here the Broglie wavelength is basically so long and it can act like a classical wave. And also all the way up to solar mass scales, where primordial black holes and very compact objects can act as matter components in our universe. And if you do a naive estimate, this is 10 to the 88th order magnitudes from the lowest to the highest energy scale or mass scales, which is a very, very big order range for dark matter, and basically singling out and exploring this whole mass range will actually be very, very challenging. So that's why we still are really heavily pursuing the experimental and the theoretical sides of which range would be the most probable. And today I'll actually be focusing more on the heavier side of dark matter, which will be more clear in the later part of my talk. And also in terms of inflation has been a very successful paradigm, being an early stage of an exponential expansion that can solve the horizon and the flatness problem of our universe, and also can provide the initial conditions for our universe as well. And theoretically, that was established quite well, but also experimentally, this can be tested. Observationally, this can be tested with the CMB measurements to a very precise level. And what we can do is, in terms of constraining inflation, what people do a lot is they can constrain it by using the primordial tilt and the 10 to the scalar ratio. So all of these cosmological observables actually can be determined through the thing called slower parameters, where the epsilon is basically the change of the Hubble rate of the universe, of that stage, and also the eta parameter, which is basically the change of that epsilon parameter as well. And what we can do is we can transform all of the observables into these kind of formats as well. Like you see, the spectral index can be expressed in this kind of format. This tangent scalar ratio can be expressed in this kind of format. And the simplest ingredient that we can use to basically have this stage is by including a scalar degree of freedom associated with some kind of potential that satisfies the smallness of these two parameters. And from there, we can actually have like a quasi-de Sitter space of expansion and have inflation. But now, because the thing that CMB measurements are so precise, we can now actually see as the figure over here, we can now be using the CMB measurements, these contours here, to actually sort of shed light on what the potential forms could be that are consistent with the CMB measurements, which is actually a very big highlight. So the CMB observation is actually precise enough to be used to constrain inflation potential these days. And this will get much, much more precise throughout the years with upcoming CMB measurements as well. Right. So with that, there was I highlighted some two problems, let's say dark matter and inflation. So for dark matter, we need something in that 10 to the 88 order of magnitude mass range, which can be heavy and light, of course. But also for inflation, we need a scalar degree of freedom to basically simply explain the concept of inflation. So the question, the natural extension that we can think about is, we know a scalar particle in our particle physics models. It is the Higgs boson. So why don't we just use this Higgs boson, identify a potential associated with this Higgs boson, and see if it can explain our inflation, and see if it can also explain some other problems that we didn't really think that it would also explain as well. And among a lot of models that involve the Higgs as the inflaton, I would like to focus more on the Higgs R-squared inflation framework today, which I would explain like later into the talk as well. So this is basically the spirit of why I'm considering the Higgs as a part of our inflationary scenarios as well. So the outline of my talk from here will now be introducing the Higgs R-squared inflation, but also including a very essential part of, let's say, the standard model, especially because it's a quantum theory. There will be couplings that are different values with different energy scales. Including that with all those effects, what we can see is that it will give successful inflation, but also what it will give is some observational consequences in the form of dark primordial black holes, which can actually be a component of dark matter, and actually can be the majority of dark matter, but also associated observables in the sense of gravitational waves. Yeah. So with that, there are some terms that are here. So let's start with the Higgs R-squared inflation. But before we go into that, let's just see if this Higgs itself can just be our inflaton without any kind of extension. So what we can do from here is that we can just write down an action that that utilizes the Okay, this is sorry. Yeah. Sorry, this. Okay. Okay. Great. Yep. So yeah. So let's just review what the Higgs itself can be in terms of inflation. So we can write down an action in this kind of format. So there will be the Higgs over here. There will be a potential associated with this. But also you can see that in terms of renormalizable operators that we can write in the action, it's all up to dimension 4. So another operator that we can write is actually this dimension 4 operator with the Ricci scalar, and that is coupling with this coupling strength, which we call the non-minimal coupling constant. And from here, we can actually transform this into a more manageable form. We can transform this into Einstein gravity using like a so-called conformal transformation. From here, what we can get is this kind of potential. So this will be the potential that is associated with a single field Higgs inflation, which you can see over here is this kind of format over here. So for larger Higgs field values, it reaches a plateau. For smaller field values, it goes into the reheating phase as well. And if you are familiar with inflation, you can see that this potential is actually, in terms of a classical sense, it's equivalent to a Starobinsky model. And if you are also familiar with the CMB measurements, the Starobinsky models are actually the ones that are well within consistency with the CMB right now, and actually can be further tested with future CMB observations. So successful inflation, but there are actually several theoretical issues that can reside. In order to match the size of the curvature perturbations that are measured by the CMB, this ratio that is actually determining the height of the potential has to be some sort of value of the order of 10 to the minus 10, which if we just think of it, of the lambda as a dimensionless coupling, and we just give it to be like order 0.1, nominal coupling value has to be very, very large. During inflation, this is not usually a problem. But actually, this will be a problem when we go into the preheating stage, because at the vacuum over here, we can actually calculate the cutoff scale of how well this theory is perturbatively consistent in some sense, predictable. And that cutoff scale is scaling as m Planck over the non-minimal coupling value. So for a large non-minimal coupling value, the cutoff scale is actually very lower than the gravity scale. And if a lot of studies have been searching this region, in the sense that they were analyzing the preheating stages of single field Higgs inflation, and the energy processes that are associated with the preheating stage actually exceeds this cutoff scale, making it basically invalid in terms of a theoretical sense. So that has been dubbed the unitarity problem, and that has been actually been extensively studied throughout the years. But also, so in order to evade this problem, you can basically take two approaches. You can either lower the non-minimal coupling in the sense that it will be like order 1, but then the lambda over here has to also be suppressed to the same extent to be, let's say, order 10 to the minus 6. Is it really natural to think about that kind of value? Well, if you really think about the standard model, it's actually quite possible in the sense that if you consider the running of the coupling, these very, very small values of lambdas can be achieved, and also can save the single field Higgs inflation scenario from this issue. But also another approach that you can think about is adding additional scalar degree of freedoms, which will actually alter this cutoff scale during the preheating stage, and basically save the theory from perturbative, let's say, non-perturbative effects as well. So that can be achieved by, let's say, adding additional scalar degrees of freedoms, and that is actually the spirit of the Higgs R-squared inflation, which is over here. So by adding additional scalar degree of freedom, we can actually write down a Lagrangian in this kind of format. Notice that the scalar degree of freedom over here is not like a standard particle context. It is associated with the R-squared term, the Ricci scalar squared term, which is also dimension 4. So it's completely reasonable to consider this in this renormalizable context, and it's a very plausible UV extension to the Higgs as well. So now there is a non-minimal coupling, the scalar degree of freedom, and also Higgs over here. And we can also do the same thing again to basically change this into a manageable potential, which will now include a scalar degree of freedom over here, which we dub the scalaron, the Higgs, and also the nominal coupling and the self-coupling over here as well. And notice that over here, I just wrote lambda as a constant, but actually over here, I'm now writing the lambda as some kind of function that is dependent on some mu, some energy scale. And because of this, what I would like to show is that this potential can now feature two features. One will be a near inflection point in the trajectory of the inflaton, which can lead to observable consequences. And also another feature that can happen is there could be a tachyonic hill where the trajectory of the inflaton follows, which can also lead to some observational consequences that we can see and actually try to use to test this scenario as well. Right, so diving in a bit more into this change of the lambda, we can actually see this in this figure over here. So because this lambda is just governing the strength of the the Higgs self-coupling, any kind of correction to that in terms of loop orders will basically change the actual value that we measure, the actual physical value. And the interaction that is governing the loops will basically govern how large the change will be in terms of energy scales. And the biggest parameter that is that governs this in terms of the standard model is actually the top quark Higgs at the top quark mass, because this is governed by the the Talcott Yukawa constant. So in electroweak scales, the lambda could be fixed to like be 0.1. But from there, if we just follow the track of this the energy, we can see that the lambda value actually runs to different values. And depending on actually the size of the top quark mass, it can either go into negative values, or it can actually reside in very, very small values near 10 to the 17 GeV. So both scenarios are actually possible still in the standard model in a 2 sigma, 3 sigma consistency. And if we just focus on this region where we consider the lambda to be positive and to be very, very small, we can actually approximate the lambda to be in this kind of format, because around here, the first order log corrections are actually very, very suppressed. So we can just parameterize this the self-coupling in terms of a minimum value and then this log squared term with some coefficient in front. And for the standard model, the lambda min is usually around 10 to the minus 6, which is actually the value that is quite needed for like a scenario where the non-minimal coupling is quite small. And also this B, which will be governed by the beta functions that are also governed by the interactions that alter the self-coupling value, is around order 10 to the minus 5. So if it's around this, if these values are around this order, we can actually still consider it to be quite consistent with the standard, still within consistency with the standard model. And with that, there was also another parameter in the Higgs R-squared inflationary case, which was the non-minimal coupling. So depending on the order of the non-minimal coupling here, which actually doesn't really have a theoretical bound on how large or how small it should be. If we just take it to be about order 100, we can actually see that there is like an inflection point developed inside the valley of the potential, where this this inflection point will lead to a phase of ultra slow roll. But also, if we just see, if we choose different values of non-minimal coupling, we can now see that there is a trajectory of the inflaton that actually follows the region where the potential is actually is tachyonic in some direction, where perturbation can grow exponentially, which will all lead to enhanced curvature perturbations. And in terms of phenomenology, these will lead to production of primordial black holes and gravitational waves. So in just like a brief summary of primordial black holes, these are actually black holes that form through the collapse of large overdensities, mostly in the early universe. And the criteria of this large overdensity has to be about order 1 in order to have like a copious amount of primordial black hole to production. And because this is considered as perturbations inside a causal horizon just all collapsing into a black hole, the mass of the black hole will actually be proportional to the size of the Hubble horizon of these perturbations. So you can see this in this figure over here. As time evolves, as the Hubble horizon becomes larger, the perturbations that are like smaller in Hubble radius will enter the horizon first. These will collapse first, and these masses will be much lighter. If the perturbation is expanded over a larger Hubble horizon, these will actually lead to larger primordial black holes. And the ratio can be actually computed in this kind of format. So for a solar mass black hole, the wave number, the cone wave number is associated to be around 10 to the 6 megaparsec inverses. And also, in terms of a curvature perturbation, in order to have this copious amount of density contrast, to have an abundance of primordial black holes to be significant, the curvature perturbation actually has to be around order 10 to the minus 2. This 10 to the minus 2 is actually quite robust in the sense that because primordial black hole productions are actually very, very sensitive, it's an exponentially process. Even a slight change in this curvature perturbation will basically alter a lot in terms of the primordial black hole abundance. So we can just take this as like a quite robust lower bound on how how large the curvature perturbations have to be in order to have any kind of primordial black hole production. So in terms of constraints, this has also actually been tested quite a lot and are up to this point. So because primordial black holes are black holes, we can actually put some evaporation bounds through Hawking evaporation, which now like constrains this side over here. There's also microlensing bounds because these are compact objects. We can actually put bounds on how abundant they are. There are also some other bounds like the CMB bounds, gravitational wave bounds, a lot of bounds associated in this mass range. But an interesting thing over here is that in this region, there's still no constraint that is actually copiously like testing or actually constraining the abundance of primordial black holes. So this mass range is still allowed to be the majority of dark matter in our case. So that's something that is quite interesting. But also because this process is associated with a very, very large curvature perturbation, what is also associated with this is actually second order gravitational waves, and which are actually stochastic gravitational waves that couple in terms of perturbation theory in the second order, and the density fraction of gravitational waves can be computed with this formula, which is just some integral that is proportional to the power spectrum squared. And you can see over here that a lot of future and current gravitational observatories are actually putting bounds on this constraint. You can see LISA over here, DeSigo over here, LIGO over here. And of course, just this June, there has been results from PTA results, which they report a stochastic process. So, and you can see that the value that these go down are up to 10 to the minus 16. So if we do like a naive estimate on how large the gravitational waves will be associated with primordial black holes, we can use this order of estimate, where it will be 10 to the minus 6 times the power spectrum squared. So if we just plug in the power spectrum to be 10 to the minus 2, this is about order 10 to the minus 10. So if you see over here, it's well in reach with a lot of future proposed gravitational wave observatories. So that is also like a very promising future that we can actually test the abundance of primordial black holes and inflationary scenarios that are associated with it, also using gravitational wave observatories as well. So with that, I would like to now dive back into the Higgs R-squared inflation and see like each scenario. First with the ultrasloral, which just to remind, the non-minimal coupling is around order 100. If we just follow the trajectory, we can now express the potential in this kind of form, where there's this kind of inflection point along the trajectory. In the larger field values, there's the CMB plateau, which will just resemble slow roll inflation. So the curvature perturbation will power spectrum will just be proportional to these values, where the both slow roll parameters are actually very small. So, and that will give the CMB observables. But also near inflection point, because it's very, very flat, the epsilon parameter will actually be very small, like order 10 to the minus 6 as well. It's just because that this potential is so flat that the velocity of the inflaton will just be very, very small as well. But in addition to that, because this velocity is so small, now it can actually be comparable in terms of the acceleration magnitude of the inflaton, which now leads to an eta parameter to be actually of order 1 or so. So in terms of this formula, you can see that there will be an enhancement in the curvature power spectrum because of this small epsilon, but also because of this order 1 eta parameter as well. If we look at the evolution in terms of the field, we can actually see this over here. The S will be the scalar on degree, the H will be the Higgs degree, and you can see that up to this point, it's just standard slow roll inflation. However, once it hits that inflection point, the inflaton slows down and just stays at a specific value for like order 20 e-folds. That will lead to the enhancement in the curvature perturbation that we can actually compute over here. So in larger scales, it will be just the CMB, but at smaller scales, there will be this peak where the growth of this curvature power spectrum is actually of order k to the fourth. And you can also see that this matches about 10 to the minus 2 as well. So from here, we can actually compute the primordial black hole productions, which is listed over here. And you can see that because it can reach order 10 to the minus 2, we can actually have a significant amount of primordial black hole productions in principle and in various mass ranges. But the problem is, it also has to be consistent with the CMV measurements as well. And because the ultra slow roll is taking away like 20 e-folds from a normal 60 e-fold inflationary scenario, the CMV observables will also shift accordingly. So we did like some kind of scatter plot by changing the parameters and see how the trend will change with the slow roll parameter NS and the primordial black hole mass. We can see that actually there's a difference in the sense that it's shifted and it's in tension in some sense up to like 2 sigma with the CMB, which can actually be used to test this model as well. If the CMB measurement becomes much more precise, then at least the ultra slow roll scenario of a primordial black hole production in Higgs R-squared is ruled out. So ultra slow roll, that's all gone. Let's say tension with CMB. Now, if I move on to the next part, the tachyonic instability, let's just see that here now, because it's there are 2 degrees of freedom in the theory. There will actually be like a turn that is not associated with like one single valley, and it will actually be a multi-field effect. And we will see that the perturbations will actually grow exponentially as well, which is actually quite a different feature from the ultra slow roll case. So yeah, in order to do that, let's just plot the potential, a slice of the potential, and change the field value of the scaleron. So if we see over here, this is the Higgs direction, and this is just the potential. And I don't know if this will work, but let's see. Yeah. Oh, yeah, there it goes. Yeah. So you can see that as we change the value, there has been like a potential that had like significant 2 valleys, but then it developed into like 2 different valleys at a smaller value. So on the right, you can see this trajectory where you can see that over here, there is this black line is the trajectory. It can initially follow a valley that is effective single field, but because the potential is changing with the field value, and that is all associated with the running of the Higgs coupling, another valley can develop down over here, and the trajectory can actually follow this tachyonic hill. I don't know if you can see over here, but like this bump. And depending on how long it stays over here, the curvature perturbation can grow a lot. And from there, because it's not exactly at the top, it will just fall down into one of these valleys again, just basically leading to a very temporal phase of enhanced perturbations. So if we decipher that a bit, let's just start with the valley up top over here. If we just follow this, there will be the CMB point. And then from there, it will just follow this valley until the point where the potential is actually, like, this is not the local minimum, and we'll start rolling down into this phase. And from here, because now this is a local maximum, it will just slow down. It will follow this hill over here. And you can actually see that because it's tachyonic, you can see an exponential growth in this green line over here, which notes the isocurvature perturbations, which is basically the orthogonal perturbation directions of the travel of the trajectory. And the perturbation equations that govern this phase will just be enlisted over here, where you can see that it involves the Hubble expansion, so the wave number, but also this m effective square over here. But because this mass like this mass squared here is negative, this overall component can actually be negative as well. And if we just solve this naively, we can actually get this exponential expansion in terms of the power spectrum, which is defined to be this. And you can see that this trend is just basically like a very exponential growth over here. But to be honest, this is the isocurvature perturbation. So in order to have like primordial black hole production and so forth in our universe, is usually associated with the curvature perturbation. But that can be transferred, this enhancement can be transferred into the curvature perturbation, this blue line over here, because now it will be turning again back into another valley. And you can see that the curvature perturbation is actually enhanced after this tachyonic phase, just because the inflaton is now starting to turn. And it will have like a mixing between the isocurvature and the curvature perturbations, leading to this exponential growth in the curvature perturbation as well. And then once it falls into the valley, there will be this substantial mixing period over here. Once it falls into another valley, the mass squared actually now becomes positive again. So the isocurvature mass will just, the perturbation will just decay again. However, the curvature perturbation will just freeze out, and this will lead to the observed power spectrum at the end of inflation as well. And you can do this for every mode that is exiting the horizon at different field values. From there, we can actually clutter everything and plot the final curvature perturbation power spectrum at the end of inflation by changing different, parameters. So for this plot over here, I fixed the scalar on mass, which will actually just govern the height of this curvature perturbation at the CMB scale. This beta 2 will be 0.5, which will lead to the B parameter that I said before to be about 10 to the minus 5. And I changed the lambda values, however, still fixing it to be about order 10 to the minus 6. By changing the values of the non-minimal coupling, we can get different peaks at different wave numbers. So a feature of this is that there's actually universal CMB predictions over here. CMB is fine. There will be no tensions with CMB. It will give the right normalization and also give the right spectral index and the tensor to scalar ratio. But depending on these values, this peak can actually move with quite a lot of scales, so which are actually accessible from pulsar timing arrays all the way up to LIGO Virgo and actually to values much larger scale and also smaller scale as well. One thing that I have to mention is actually that this scenario is also quite tuned as well, because it will actually, the exact parameters will actually govern on how long the inflaton will stay in this tachyonic stage. If the values are a bit off, it will just fall back into the valley again prematurely, and it will just reduce the height of this curvature perturbation enhancement. And we can see that in this figure over here, we can actually see that the degree of tuning that is needed to have like the amount of primordial black hole production is around 10 to the minus 4%. So in terms of digits, about 10 to the minus 6, which is tuning. It is still tuning, but still it is in the same order of single field ultra slow cases as well. So it's still like not as severe. It's not a more severe tuning than we expect. So by using these curvature perturbations, we can now go on to the phenomena we can actually associate with these primordial black holes. You can see 1, 2, 3 over here, varying in different mass ranges. And you can also see from here that like some are around order, like diffraction is around order 1, some are actually order 10 to the minus 4. And you can see that this is actually a consequence of the sensitivity of primordial black hole production. And you might have noticed that over here there are 4. Why is there only 3 over here? Because the 4th one is just hiding down below. But also in terms of second order gravitational waves, these can range up to different values. But also this feature in the spectrum, and which can actually be used to actually compare between the ultra-slow case and usually sort of break the degeneracy between the ultra-slow case and this tachyonic case as well. And you can see that this is well in reach of Lisa and DeCygo. So hopefully in the future, we can use these gravitational observatories to sort of test this scenario as well. So with that, I would like to sort of conclude, going back to the standard model figure over here. So in this talk, I will sort of focus on the Higgs R-squared inflation, which is an extension of the single field Higgs inflation. And the reason why we used Higgs is because it's the fundamental scalar that we have in our standard model. So it's actually quite interesting to think about this to be a candidate for our inflaton. And associating that with the running of the couplings, that is also an essential part consider in quantum theories, it can actually lead to two consequences, both like in inflation. One will be the near inflection point in developing into potential, and another one will be a tachyonic instability developing into potential. Both can lead to primordial black hole and stochastic gravitational background production, all consistent with the standard model. However, for the inflection point case, there is a tension with the CMB. And together in this framework, I just wanted to say that this could be possible signatures of the Higgs that is responsible for the electroweak physics in our universe, can also be responsible for things much higher scales as well. And this can also be seen as an interplay between inflation and the standard model of particle physics. And this can actually be tested in both ways by looking at the particle physics sector and also in cosmological observables as well. And with that, I would like to end my talk. Thank you.
Thank you, Dhong Yeon, for a really nice talk. If people have questions, please raise hand. And while people gather their thoughts, I have some questions myself. So you mentioned in the talk that this non-minimal coupling parameter, there's no really good theoretical bounds on this, what parameter range this can have. And so like you showed like two typical behaviors when there was order of 100 and order of 1 for ultra slow and tachyonic instability. I was wondering how wide the rough range of this I values for each of these behaviors to happen, and also if you have investigated at all what happens like in ranges that are completely different from this, like so like 10,000 or 10 to the minus 2 or something like that.
Right. So just a disclaimer, I would have to say that there are several theoretical things that do sort of constrain the range of nominal coupling, which is not like super constrainable, but like things like if we just think the single field case, the unitarity problem could be thought as a constraint of how large the nominal coupling could be. Also, in the Higgs R-squared term, actually because it's like this R-squared can also be induced from non-minimal coupling loop effects. That could also put a bound on the nominal how large nominal coupling could be, or how large the scalar mass would be associated with the nominal coupling. But yeah, just as a phenomenological thing, most of my like reasoning was actually just from the observational consequence. So if in a single field Higgs inflation case, the nominal coupling observationally will be constrained by that ratio, the lambda over psi squared. But actually in the Higgs R-squared, because they are, if I go back to the slide, let's just see. Yeah, because there are two degree of freedoms over here. Basically, the interplay between these two degree of freedoms will actually determine the height of the potential, consequently the values of CMB observables. So in here, the regime that I'm actually focusing on is that this M parameter, the scalar mass, is dominant in terms of determining the CMB, at least observably. So in that sense, the nominal coupling could be, doesn't really have to be restricted to that lambda over psi squared. It doesn't really have to be restricted to that. It will just be a combination of this plus the mass of the scalaron being that, being the CMB normalization. So in that sense, this psi can be like any kind of value independent of the lambda value. However, in terms of achieving this features of the of this let's say near inflection point and also the tachyonic hill, it does have to be in that order. Let's say if it's order 1,000, let's say there could be an inflection point, however, it will not be matched with CMB observables, and like just in the sense that it will like tend to give like too long or like too short ultraslow phase. But also in the sense of the tachyonic hill developing in the trajectory, that also has to be about order 1 as well. So in terms of the phenomenology that is associated with that, at least in the parameters that we consider, those have to be about that order. And yeah.
Right. Thank you. I think I understand it better now. Rodrigo has a question.
Yeah, thank you for the talk. It's really interesting. I was wondering, maybe this question might be a bit naive, but so the action you're showing now, it's basically in the Jordan frame. But if I
Right.
remember correctly, once you move into the Einstein frame, then this your scalaron, because you moved into another frame, your standard model fields will be coupled to this new metric, right?
Right.
So is this possible to put constraints from particle physics from the coupling of these standard model fields to the G mu nu in the Einstein frame and constraint from this type of scenarios, or is it?
So if I understand correctly, so yeah, so how should I say? So to this point, everything is in the Jordan frame, and we can transform that into the Einstein frame as well. And there will be this basically this will be governing the coupling between, this potential will actually be governing the coupling between scalaron degree and the Higgs degree, right? So in terms of direct particle physics context, let's say just putting a generic bound, I guess, was a bit too hard. Just because like the things that are associated with the things that are associated with the scales of, let's say, particle physics experiments in the electroweak are a bit too far off from things that are associated with the scale of the scalaron. However, in principle, let's say in terms of inflation, in terms of particle physics, what we can actually do is, let's say, just change the values of, let's say, the Tokamak mass and everything, as I showed before, and see if this is just compatible with, like, in terms of inflation, if we want this to be inflation, compatible with like a certain value of scalaron degree of freedom. That we can actually just put like a constraint from that. I don't know how, to be honest, I don't really know how sensitive it will be, but I think in principle it should be possible. Yeah.
Okay, thanks. If no one else has questions, I have another, if I may.
Go ahead.
Yeah, so if you go back to, I think it's slide 33, 34 or something like this, when you
Right.
show the enhancement of curvature perturbations. Yeah, there. So I think that if I understand correctly, the fact that you move in this orthogonal direction, that enhances your isocurvature perturbations.
Right.
One first question is, what are these dashed lines that you show?
So yeah, I should have been a bit more rigorous on that. So let's first focus. Oops, sorry. Let's first focus on these two dashed lines. These will just be the region where the tachyonic, the mass becomes tachyonic in some sense. You can see that this corresponds to this line over here. This black line, this black dashed line or dotted line, is actually the the time, the time when this perturbation actually leaves the horizon. So so depending on like each stage of inflation, the perturbations will leave the horizon at a different scale. So let's say, for perturbations that, let's say, are associated with the CMB will leave the horizon much earlier than this whole tachyonic stage. The isocurvature perturbations will be much more suppressed, because just it has much longer time to be suppressed. So in that sense, the features will actually not be how should I say, affected by this tachyonic phase. However, perturbations that leave the horizon near this tachyonic phase, let's say in terms of, let's say, this isocurvature perturbation, it will just not have enough time to decay enough, in the sense that it will hit the tachyonic phase, the perturbation will now grow exponentially, and then lead to this overall enhancement compared to just the CMB case as well. So yeah, in that sense, this black line is just denoting when this specific perturbation is leaving the horizon. So that's why the K over AH is actually just 1 to be over here.
I see.
Right.
I see. So that means that the second vertical line,
right.
So basically, is it correct to say that these perturbations would be entering much later on in the history? So maybe we can see them from LSS, or is it incorrect?
Yeah, so in principle, like these features that are associated here are in much smaller scales. So in terms of entering the horizon again, it will happen much earlier than the CMB. So it will be associated with much smaller scales. Yeah, so if this feature has been, let's say, much closer towards the CMB, maybe we could see some other like observables, but at least what's going on over here, let's say, it would just be things that are much into the smaller scale than anything that can be probed up to this point, except for hopefully gravitational observatories. An interesting thing is, yes, this tachyonic instability can actually develop near, let's say, smaller scales that are accessible, I guess, with that are scales that are a bit smaller than CMB. However, in terms of, there are already like constraints over there, as if I remember correctly. So in terms of producing black holes for dark matter and having like a very large gravitational wave background, that will already be constrained. Right.
Ask one selfish question, I guess. Have you ever computed 3-point functions in this case? Would they be enhanced at all?
Right. So in terms of computations, no, we did not. Just because, let's say, the phenomenology that we were interested in, let's say, in terms of the tree level, were the 2-point correlation functions that will be associated with the curvature perturbation, primordial and gravitational waves. Yes, in principle, I think there will be some interesting phenomena that are associated with this, like in terms of the non-Gaussianity, the 3-point function. However, at least in terms of the CMB, because it's almost similar to just the effective single field inflation, there might not be any like noticeable signatures. However, but like at least in terms of this stage, there could be some non-trivial spectrum, just because there are terms associated with this, which actually has been studied quite a lot theoretically as well. But yeah, there might be some interesting phenomena associated with that, but we didn't really compute that yet. Yeah.
All right. Yeah. It sounds like even if there is, it will not be in the CMB. So
Maybe, yeah.
right. Cool. Are there any other questions? If not, shall we finish the recording here?